clock speed of a processor, but you can have, say, teraflops, which is 10 to the 12th floating point operations per second, petaflops, which is 10 to the 15th, which is about the scale we're at right now in our supercomputers, and then exascale, or exaflops, which is 10 to the 18th floating point operations per second. And this picture shows, on this log scale, some of the history of these computers, starting with those Cray computers that I talked about that were the same power as your smartphone is today. Now, this computing performance didn't come kind of for free. There was a lot of hard work that went behind it. Some of that had to do with Moore's law and the shrinking of transistors, and some of it had to do with figuring how to use new kinds of architectures. So in the 1990s, we went through a transformation called the attack of the killer micros. This is when we realized that we really couldn't, that the people that were trying to design these special purpose Cray supercomputers, which were vector supercomputers, really nice and easy to use. The scientists loved them, but they really couldn't compete with the fact there were all these other companies like Intel and IBM and AMD and so on building microprocessors. And the microprocessor designers had a bigger market and more people to design them, and the people building the special purpose supercomputers couldn't really keep up. And so we started building our supercomputers by putting a network of all of these microprocessors together. And that's really still what we're doing today. So the difference between one of our supercomputers at a center like NERSC and some of the kind of clusters that you have inside of your departments is not very big. It's something like the integration of the network, maybe a high-speed file system, but the architectural components, the processors and the memory are all standard building blocks. Now, the other thing that, of course, is a big transformation is the advent of multi-core processors, and that happened because of the heat density on the chips. We couldn't continue making processors any faster, and so maybe oversimplify things a little bit, but it meant that the rest of the world had to worry about using parallelism. And the transformation that we're about to go through, I like to call attack of the killer cell phones. And that's because it's really about how to build computers in an energy-constrained environment and how to get more performance out of computers in an energy-constrained environment. So sorry, some of the slides didn't translate over here very well from an Apple to a PC, but this says that computing performance growth has been invaluable in science and in business and society, and we need to figure out how to continue to increase the performance, but it's going to be much harder to get the next order of magnitude or 3 orders to computing performance than ever before. So why is that? Well, energy efficiency in computing is really going to be the key to performance growth. As I mentioned before, a megawatt of power costs roughly $1 million a year to run. So if you've got a megawatt machine, and it would cost you $1 million a year to run it just to pay the power bill. Our supercomputers, our petascale systems, use a few megawatts today. We installed one in 2010. It was a 3 megawatt computer named Hopper, very popular with the scientists. If we tried to build an exaflop computer and we didn't get any energy efficiency improvements, that would be a 3 gigawatt computer, which would require that we pay $3 billion a year in our power bill, and we certainly do not have that kind of money. Now we do still have Moore's law effect going on, at least for the next several years. And so we get when the transistors shrink, you get more compute for with less power, and that makes the systems overall more energy efficient. But we did a projection back in 2010, looking at what would be required to build an exaflop computer in 2018. And what you see there is this red curve that projects out kind of where we would be at with the traditional improvements in energy efficiency that come from Moore's law scaling. Now, that got us to about 130 megawatt computer. I think we're getting a little bit closer. We've moved along that path a little bit, but what we would like to get to now is what we'd like is a 20 megawatt computer. So that would be kind of a $20 million computer. As I mentioned, that's about the same amount of power that a Google data center uses. So I can at least imagine putting that much computing into one computing facility. And notice that if you don't really care about big computers to solve big problems like climate change or combustion simulation, it doesn't really, this equation doesn't change. If I said what I really want is to put 100 of the 10 petascale systems in each one of the 100 top universities, top computer science departments in India, it's still the same amount of power. And so the real question is, how can we improve that power? So why do we call it Attack of the Killer Cell Phones? I like this picture because it graphically gives you an idea of the difference between a cell phone processor and a server processor. So the larger picture there is the Halem processor, 4-core processor, and the one on the left is a cell phone processor. The server processor is much more powerful, over an order of magnitude more floating point operations per second. It does 50 gigaflops as opposed to only 4 gigaflops for the cell phone processor. However, you can also see that there's a huge difference in the size, the amount of area that each of those processors takes, and there's also a 3 orders of magnitude difference in the amount of power, with the cell phone processor being much more energy efficient, consuming much less power. So so overall, then, the energy efficiency of doing those floating point operations is a factor of 100 better on the cell phone than it is on the server processor. And that's true kind of independently of the types of systems that the specific processors that you look at. The reason is that cell phone designers are really motivated to design things that are very energy efficient. Now, that doesn't mean that they don't care about performance. If you want to be able to talk to your cell phone, then it has to be able to do speech processing in real time. And you need to be able to process these signals and stuff very quickly, but they have a, which is the amount of power that your cell phone draws. Now, I thought that the main reason that cell phone designers cared about power was because of battery life, and it is true that battery life is a big consideration for them. But in talking to one of the people that designs these, they said the other big reason is because nobody likes to carry a hot cell phone around in their pocket. So for the same kind of reasons of heat density and cooling that we worry about when we're building data centers, you also worry about this when you're designing cell phones. And so the idea is that if you want to very energy efficient design, you should talk to people that design cell phone processors, not necessarily the people that design server processors. Now, that's not to say that we're going to build a supercomputer out of your cell phones and just kind of hook them all together, although people have tried. But it doesn't seem like a very efficient way to build a system that you're going to try to program as a single unit, and it's actually pretty hard to program. So we see this idea of energy efficient processor cores in things like the Xeon Phi from Intel, the Knights Landing, Knights Corner, and so on line of processors. And we also see it inside of GPUs. The GPU processors are somewhat less general purpose than the ones in the Xeon Phi. Maybe there's a little bit of a performance advantage. So there's a couple of approaches that people are using in terms of the architectural models in order to get to this kind of energy efficiency. And there are other things that people are looking at as well that are newer architectural models, including more reconfigurable computing or more special purpose computing. So the point of this, though, as somebody who is a programming language designer and compiler writer, is if I'm going to build a system out of these little tiny processor cores, I want my programmers and my algorithm designers to be thinking about parallelism all the time. Because if they're thinking that they're kind of going to run their serial code, and every once in a while there's going to be a loop nest or something they're going to run on in parallel, that's going to give you terrible performance. So the question is, can you get algorithms and applications that are basically running in parallel almost all of the time? Now, the second challenge that we're seeing that's coming from also from the constraints on designing these things is heterogeneity. And there's a picture here of both the kind of processor that's in the Stampede system at the Texas Computing Center, and also the kind of compute nodes that are in the Titan system, which is at Oak Ridge National Labs. So one of them has NVIDIA processors, the other one has a Knights Corner processor, and in both cases, these are set up as co-processors. So first of all, why are we building heterogeneous computing nodes in this space? Well, I already gave you the reason that I think we need lightweight cores. We need lightweight cores that are very energy efficient so that we can get more computing capacity with a fixed energy budget. But we also need, the concern is that we may need a few of these kind of more heavyweight processors, so traditional CPUs, in order to do things like run the operating system. And for the bits of code that we have that are not highly parallel, we may also want them for that reason. We're also seeing changes in which you can put a lot of cores on the chip, but you may not have enough power to turn them all on at once. So you may have a mixture of different kinds of cores on the chip. Now, the fact that we have these, that I see that there's a likely trend toward heterogeneity. I will say, by the way, that the next nurse system that we're getting at Berkeley Lab is not a heterogeneous system. It's going to be a nice landing system that has entirely nice landing processors throughout the compute part of the system. There'll be some heavyweight processors that are just in special purpose nodes for doing things like I/O, but each one of the compute nodes will not have a CPU and then Intel a Xeon Phi as an accelerator. It'll just have the Xeon Phi. And we're kind of seeing that kind of trend happen as well. And I think that we want to get away from this idea of accelerators where you say, well, we'll have a CPU and slap this thing to the side, kind of for the same reasons that I talked about in terms of thinking all the time in parallel and using the energy efficient cores as much as possible. First of all, on today's systems, there's a bottleneck, which is between the CPU and the GPU, PCI bus variations of that. The other problem is, as a programming model, it means that your default code is running on the CPU, which is the expensive, energy-consuming part of the system. And then when you see a piece of the code that you think, oh, I think I can CUDA, you send the data over to the GPU and you run it there. Instead, what I'd like to do is invert the model and say the whole application runs over there on the quote accelerator side. It runs the lightweight, energy-efficient cores. And if there's anything that those cores are unable to do, such as, for example, perform I/O, then they will call the heavyweight cores. And this kind of a reverse offload model, I think, is at least a better model than the current accelerator model that we're using. It is a better mindset also for people that are designing algorithms. So I actually think the coprocessor model is going to go away. We'll see better integration. There are market pressures, though, I have to say, in both directions. So this conjecture may or may not come to pass, but I hope that it will, and I hope we'll put the energy efficient cores, which are in the majority on these systems, in charge of the computation. Challenge number 3 is really about having very little memory per core. And as we grow the number of cores on the chip, which is coming in part from Moore's law, that is transistor density, as well as making the cores simpler, we are not scaling the amount of memory per in relation to that. And the reason is because of just technology trends. The memory density has not grown as quickly as logic density, and the cost of memory has not dropped as fast as the cost of computing. Now, I will say that all of these things are slowing down as we reach the limits of Moore's law, but at the moment, there's still a huge gap in these, and so we're going to see much less memory per core. So what is one of these, if we were trying to project out what makes a flop computer, let's say in about 2020, maybe a 2023, in that time frame, look like? This is a cartoon that one of my scientists, John Shaw, put together based on a lot of discussions with vendors. So he has a lot of discussions under NDA, so this is not reflecting any particular kind of design from a vendor, but sort of synthesizing those ideas. This is what the system looks like. First of all, you've got a lot of thin cores. Those are the lightweight, energy-efficient cores in the middle. However, they're not necessarily uniform, and that means that the whole node may not be cache coherent across the node, because there are concerns about getting cache coherence up to the level of, say, 1024 cores. If we're going to have 1K cores on our chip, we may not be able to have cache coherence at that level. Not that we don't know how to implement it, but that the overhead and the energy use, frankly, of doing cache coherence at that scale may not be worth it. Well, we may have some of these wider heavyweight cores, as I mentioned. We'll probably have the communication fabric on the chip, or at least on the package. So this is the NIC on board. And then we'll have some traditional DRAM probably on the system, but in addition to that, there's 2 new levels of the memory hierarchy. The first one is at the top, which are these high bandwidth memory stacks that are on the silicon substrate. So you can talk to the processors can talk to this memory fairly quickly, and also non-volatile memory that is in between the DRAM and the disk in terms of the memory hierarchy. So 2 new levels of the memory hierarchy. The top one is between caches and DRAM, and the second one is between DRAM and disk. And that's to deal with the fact that we're seeing these gaps growing, the widening gaps between the different levels of the memory hierarchy. Now, you might say, well, what's another level of cache in my system? We've been adding levels of cache on the chip and off the chip for a while, up to 3, 4 levels or whatever. But the difference is that these may be software managed. And that also gets back to an energy issue, which is a hardware cache tries to anticipate through its caching algorithms what data should be loaded into the cache based on what data you've accessed, right? It uses temporal locality and it uses spatial locality to preserve things in the cache and to load things in anticipation that you're likely to use something that's nearby something that you've already loaded. So the problem is that that those algorithms are not necessarily good predictions, especially for more irregular sorts of computations. And so you can waste a lot of energy moving things around in the memory system that doesn't have to be moved. Of course, between disk and memory right now, we already have an explicit movement. You don't just, well, on our computers at least, we don't run virtual memory systems because, and for the same reasons that they're not very good at predicting how things run, and so it tends to make the computers run very slowly. So we move data manually in and out between disk that is opening through a file and into memory. So we're going to see these software managed levels of the memory hierarchy. We're already seeing them emerge. You see them on GPUs as different parts of the memory that you explicitly move data in and out of. And I think we'll continue to see that in these systems. Now, what are we going to do about these challenges? Well, the biggest challenge that I think we're seeing, and this is really different than it was 10 years ago, is architectural diversity. Nobody is quite sure what the right model is, what the right architecture is for bringing these systems into the next generation to make them, whether you want an exaflop or you want a petascale system in a rack or whatever you want. And so people are looking at GPUs, they're looking at things like the Xeon Phi, they're looking at other alternatives, ARM cores and things like that. And so what do I think is a reasonable approach? Well, I'd like to tell you that we're just going to build a really great compiler, and we're going to take one of the languages that everybody uses a lot, such as C++, for example, or Java, and we're just going to compile that down and make it generate really high quality code for GPUs and for CPUs, multi-core systems, mini-core systems, software managed memory hierarchies, wide SIMD units, and all of these things. But the truth is, the compiler community has not been able to do that so far, and I don't see that problem being solved in time to make it, well, because these architectures are emerging today. One approach we've used at Berkeley for a long time is something called autotuners. So I'll give you a few examples of my own research throughout this talk, but this is the first one, which is automatic performance tuning. So what is an autotuner? An autotuner is something that does code generation plus some amount of search. So it's kind of giving up two unsolved compiler problems. The first reason that the automatic compiler problem failed was because you couldn't do analysis well enough on complex code. So as soon as you go to a language like C or C++ that has pointers in it, but even with a sort of simpler language in terms of the analysis problem, a language like Fortran, it was still very difficult in general for compilers to analyze anything other than really simple code. And so the dependence analysis problem meant that you couldn't automatically transform this code to automatically parallelize it in the way that you needed to. But even if we took that problem aside, we still had the problem that if you look at something like matrix multiply, it's very difficult to figure out what the optimal code is to generate. And so there's a lot of work in that area as well, things like tile size selection algorithms, but the truth is that this was a hard problem to solve. So what we do in auto-tuning is we build a special purpose code generator for a particular algorithm or a particular class of algorithms, and then we run that code on the architecture and select the one that gives you the best performance. So the little heat plot there is looking at tiling for register blocks in a matrix multiply, and you can see the little hot red one up there at the top is the value that you want. We sometimes call this looking for a needle in a haystack. If you look at these heat plots for a number of different problems, a number of different machines, they're often quite irregular. And so if you're off by a little bit, in some cases, this one's maybe not quite so bad, you will see that your performance can really drop precipitously. Now, Sam Williams, who's also the lab and actually a graduate of UC Berkeley, in his PhD thesis, because he was trying to describe all of these different algorithms and automatic performance tuning ideas, does something called a roofline model, which is a great kind of simple cartoon for thinking about performance. And the idea is you build this this little graph that has the attainable gigaflops of your algorithm and your machine, and the actual floating point operations per byte. If you don't like floating point codes, you want to do integer codes or logic codes, you can use another value in the numerator there on the x-axis. And the idea of the roofline is that the flat part of it is based on the peak performance of the hardware, and that can vary depending on what you're using all the hardware. So, for example, you're using double precision floating point, but if you're not using a fuse multiply add instruction, you're going to drop to half of the speed. If you're not using SIMD instructions, you're going to drop to by another half the speed. If you're not using instruction level parallelism, you'll drop by another half. And similarly, the bandwidth axis, which is then the diagonal part of the roof line, the sloped part of the roof line, is giving you this log scale, is giving you this flat sort of slope part. So the idea in algorithm design is to try to move things as far to the right as possible in order to view high computational intensity. But these graphs are kind of useful for letting us see how well we're doing. And as graduate students, this is really important. I tell all my students, you need to build a roof line for this part of the code. And you can build it for the network part, and you can build it for the computational part. You can see here we built one for GPUs and also built them for traditional multi-core systems. And each of those little colored things is a different computational kernel that comes up in one of our scientific applications. The red one there is EGEM, that's dense matrix multiply. It's about the fastest thing you can do on any of these architectures. And you can see that it's very high up, and it's sitting pretty close to the double precision peak performance of both of the machines here. On the other hand, if you're doing something like sparse matrix multiply, matrix vector multiply, that's entirely limited by memory bandwidth. Those little blue blobs, exactly how close you are depends on exactly what the matrix is. Those are down in the bottom left. But the point is, they're still very close to the roof line. And so what this tells a graduate student is, tell your advisor to stop telling you to make the code go faster, because it's running at the speed at which you can read the matrix from memory. And what are you going to do if you can only, you have to read the matrix from memory in order to do a matrix vector multiply. So there are a number of people working on these kind of auto-tuning ideas, and they give you these kind of great results that get you up close to the roof line. I have to say, a lot of the applications that run at NERSC are not necessarily tuned that well. But for the parts, the computationally intensive parts of it, and some of the codes are really very highly optimized. These auto-tuning ideas can give you that kind of really great performance. There's a lot of different ways you can do this. There are people looking at doing it built the old-fashioned way, what we were using originally, and a lot of the results you saw there is just building lots of scripts. So not a very attractive way in order to go forward if you want to convince other people to use these kinds of tools. There's a lot of libraries that use these, like FFTW, Spiral. There's things inside of the dense linear algebra libraries, the BLAS libraries like Atlas. And there are people looking at domain-specific languages and domain-specific kind of dynamic compilation techniques, which are some things that we're looking at. Okay. So that's kind of what's happening in the node, and auto-tuning as sort of a way of getting around the fact that I don't think even for a single node that we're going to build an automatic compiler that's going to generate all the right code for us. People are also looking at language extensions like OpenMP, and that may or may not give you the kind of performance you want, especially across architectures, but it certainly is another approach. Now, what happens if we go to the whole system? So the whole system is maybe 100,000, a million cores. We're looking at a billion-way concurrency, both adding together or multiplying together the concurrency between the nodes and the concurrency on the chip when we get to an exascale era machine. So the sort of default approach is what I call hybrid programming model, or MPI plus X. And that is that you use message passing between the nodes, and then you use some kind of shared memory programming within the node. Today, actually, a lot of the NERSC codes are written as flat MPI. That is, you just put an MPI process in each core. And in order to communicate between them, they do send and receive operations. So this can be, this model works pretty well if you have a bulk synchronous kind of problem in which you compute for a while, and then everybody exchanges messages, and then you compute for a while again. So that send and receive model is very popular in the scientific community. It's very scalable, it's very portable, it runs on all of the systems. You can get it on all of your departmental clusters, whether you've got an InfiniBand cluster, Ethernet cluster, or you've got a supercomputer that you're using from, say, a company like Cray or IBM. It's very widely used within the community, and however, it's got some overheads in it that I think I'm worried about, especially as we talk about communication within the node, but even a little bit between nodes. It's also not very convenient if you don't know where to put the receive operation. So send and receive is great in this bulk synchronous model, but if you want to send some data, or more, maybe a better example is you want to read some data in one processor that is living on another processor's memory, it can be very awkward to try to do that in a send receive model, because essentially you don't know when to say receive. In the other processor. So now within the node programming model, of course, there's things like OpenMP looking towards GPUs. We have things like OpenACC. These are pretty convenient. They allow you, at least in the OpenMP case, to write pretty straightforward shared memory code. If you're more familiar with pthreads, that would be a similar kind of a model. So they have pretty low overhead. You're just generating these instructions from the code. There's some amount of thread scheduling overhead that there's been a lot of research on, but they're not very scalable. So we're not going to run OpenMP across our entire machine, certainly not in an exascale, and probably not even at a petascale. There's no locality control right now. It is one of the things that OpenMP is working on, but you have no ability to say, I want this data to live near this processor in a very, it's kind of a secondhand thought to try to figure out how to pin memory down to processors. What you want is the ability to lay out the data structures in memory, put the computing where you want it associated with the data, and then only communicate when you need to communicate. And also in these approaches, we don't really have a single answer yet to the heterogeneous model. We've got things like CUDA and OpenACC, and we've got things like OpenMP. There's not a single unified one. I think we will get that unified model, but whether it means that you still write two different programs, one for your GPU system and one for your many-core system, say your Xeon Phi system, is not clear yet. So one of the things I've worked on for many years that PJ mentioned in my introduction is these partition global address-based languages like UPC and Titanium. So the idea in a partition global address-based language is it kind of takes the best of both worlds. That is, it gives you a global address space, which means that a thread can directly read or write the memory of any other processor's memory on the system. And it does that through, it can do that through just pointer dereferences. It can do that by writing into arrays if they've been put into the shared part of the address space. However, although it is kind of logically, you can access any memory anywhere, there's also kind of a physical performance notion associated with it that the address space is partitioned. So in the picture here, the yellow part is the shared part of the address space, but you can see the little dashed line between each processor as part of it. So there's a linked list that's spread throughout that shared part of the address space, but processor 0 can ask and can figure out which part of that linked list is nearby, and then do different computing on that than it does on things that are further away. So you can manage locality, you can manage communication, but you aren't forced into this send receive model or this bulk synchronous kind of programming model that says that you have to necessarily agree ahead of time when all the communication is going to happen. So one of the things I mentioned before, even within the node, is that we may not have cache coherence across the node, and that's pretty fundamental to the way OpenMP works. And in PGAS, it's not a problem because we don't have to have cache coherence in order to build this global address space. We run this global address space model on the largest scale systems today. It performs very well as long as the programmer carefully manages the locality of the data structures. So the idea of the important kind of key insight from these PGAS languages, and even going back to the architectures, is that you can't cache remote values. So this turns a non-scalable problem, which is kind of global cache coherence, into a scalable problem, which is only the cache coherence between the network interface and the processor. So what do I mean by that? If you are going to do a remote read, for example, of a value that lives in another node in the processor, a message will go across the network that says read this particular value in your memory system. It is important that you get the value out of the cache on that side, so the network interface that is managing that communication needs to go and get it from the cache. But if you get a copy of that, that is your own software copy of it. It is not a hardware copy. It's not living at that logical address in memory. It's another data structure that is your job as an applications programmer to manage, which means that it's not something that the cache coherence says that you have to manage. So now we could get this by doing message passing. MPI has recently adopted a lot of the ideas from this PGAS model and something called the Onesided specification of MPI. Actually, it's been in MPI for quite a while, but they've redone it yet again to try to make it work better and more like the way it works in these PGAS models. But this is what it would look like if you just wanted to do bulk memory operations in between, say, different parts of the address space in a language like UPC. And this is what it looks like. There's two different ways of doing that. And this is what it looks like if you put in MPI. Maybe it's a little hard to see because I gave you two examples in the UPC case, but there's only three arguments there. There's a source address, a destination address, and a size. And in fact, if you don't even have, if you wanted to send a single word of memory, you don't even need any of that special syntax. You can just say star P equals or P equals A of I or whatever. So much more convenient, but more importantly, perhaps from a performance standpoint, is there's a lot less decoding of what that whole operation looks like if you're just doing a single, you just have a couple of pointers and a size. Whereas in MPI, for generality reasons, all of these other things like data type, specifications, which allows you to pack and unpack the data, and that's very convenient for certain applications, but will make it really hard inside of the memory system to be able to get reasonable performance out of that interface. So The next thing I want to talk about is kind of a whole set of things around communication. And I've already started saying a little bit about data movement in the system and how this is expensive. But in general, communication is expensive, not just in the amount of time it takes. And we've seen these annual improvements diverging between the processor performance, and now I'm thinking about aggregate processor performance of a multi-core, many-core chip, and the latency or bandwidth of between chips. But the other thing that just mentioned here, the bottom graph is showing is that there's also a big difference in energy consumption. And so it may be a little hard to see at this scale, especially if you're sitting in the back of your rows still. But the arithmetic performance gives you about an order of magnitude or more. It can be done more with less energy. Sorry, an order of magnitude less energy than any kind of a data access that goes off chip. So the big cliff in terms of energy consumption is not going between nodes of a supercomputer. It's going off of your processor chip, outside of your cache, to something outside of that. So there's a number of strategies that we can use for this. We can use latency hiding techniques, and that's one of the key ideas in these PGAS languages is to try to hide latency. But also we can try to avoid that, and we may want new algorithms that reduce the amount of data movement fundamentally. Latency and bandwidth, you could say, well, we should just design different kind of computer systems, but that's very hard to do because latency is fundamentally about the speed of light, and there's nothing we can do to change it. And bandwidth is about money. And maybe you have enough money that you can put more cables into your supercomputer, but when you actually are trying to buy these things, you can see that even if you put almost all of your money into the network, you wouldn't have something that would really address this problem that it's still very expensive to send data. Okay, so what does this kind of one-sided communication model, which is what you get with these PGAS language, give you in terms of making communication faster? So the first thing we're going to do is try to make communication faster. And the little cartoon here is showing you the difference between two different kinds of communication that you can do in these systems. A two-sided message at the top, it's got a message ID and some data that you're sending, and a one-sided put message at the bottom, which has got an address and some data, the same amount of data that you're sending. So the difference is that when these messages go across the network and land at the network interface in the other processor, remember that may be a chip in some future design on the processor chip. Fundamentally, the problem is that the semantics of the MPI, the two-sided message, the send and receive message, it doesn't contain the information about where that data payload needs to go in memory. Right? So what happens is send has a message ID in it. Here's a send that's coming from a particular processor. There's a receive that somehow has to match that send. So look for a send that's coming from this processor. Maybe there's a wildcard or whatever, but there's some matching that has to happen. And the information about where to put that data payload is sitting on the host CPU on the other side of the network. And so some kind of coordination and synchronization has to happen in order to get the data into its final location in memory. As a result, what happens in the MPI implementation is for certain size messages, you're gonna make a temporary buffer and write directly into that temporary buffer, so you get the effect of one-sided communication, and then later you'll copy it so that it adds a copy overhead. In other cases, if the messages are larger, you don't want to pay for the copy overhead, run a little protocol to say, can you give me the actual, can you find basically where the message is supposed to go and get a location for that, so you can do a one-sided operation as well. Whereas a one-sided put is fundamentally kind of closer to what the hardware is actually doing. It's just sending the data over there, it has an address, and the network interface will pick that up and will write it directly into its final place in memory. The trade-off here, and there is one, is that there's no implicit synchronization in the one-sided message. The data just goes over there, gets written into memory, and you as a programmer need to keep your data structures synchronized. However, this can be very useful for places where you know ahead of time where your data structures are going to be and they're going to be filled in. You've kind of built all that information up in your global address-based model where the addresses of the remote data structures are. This is the kind of performance difference that you see between one-sided and two-sided communication. This is on one of the computers at NERSC named Hopper, which is a Cray XE6. Other systems have very typical sort of characteristics. We're showing here both the Berkeley and the Cray implementation of the UPC language, which is one of these PGAS languages using this one-sided communication model. Those are the blue curves. And the MPI implementation also highly optimized by Cray. And I have to say, this is not a bad MPI implementation, but that's the green curve, which is significantly lower. And the reason is because there is this protocol overhead in MPI. You have more information when you say receive than you do on a put, because when you say receive, sorry, that also synchronizes that the data has actually been received. So and that, as I said, this kind of performance characteristic is what we see across a number of different architectures. And the important thing is, in either case, you send a large enough message. This is a benchmark, sorry, I should have said this, we call the flood benchmark, where you're sending data from one processor to another processor, so just two processors in this particular benchmark. You're sending it as fast as you can, one after the other, to flood the system. When you're sending really small messages, in either case, you can't hit the bandwidth of the network because there's too much overhead of getting the messages up the door. When the messages get to be large enough, it doesn't matter whether they're one-sided or two-sided. You hit the peak bandwidth of the system. Something a little weird happens in the Cray implementation there at the end. That's sort of a protocol issue. Maybe it's a TLB issue, but in all of these, generally they will saturate up to the peak bandwidth of the network. But where there's really an interesting difference is in the middle there. So when you have, say, a message of size 512 to a couple of kilobytes, there's a huge difference in the kind of bandwidth that you get, and that has to do with the fact that it's a lighter weight protocol to send a one-sided message. Now, challenge number 7, though, is can we do a better job to not do so much communication? Can we do it with better algorithms? And for this, I'll go back to the example that I talked about before, sparse matrix vector multiply. If you remember that roof line plot that I showed you before, sparse matrix vector multiply was up against the roof line, but way down at the bottom left-hand corner because it was limited by memory bandwidth. And in fact, a graduate student many years ago, Rich Wudick, who's now on the faculty at Georgia Tech, came to us and said, when he was still a graduate student, said, well, you know, I just did a measurement and I realized that the time it takes to do a matrix vector multiply, once I've highly optimized it with my special autotuner, OSCE, is basically equal to the time that it takes to read the matrix from memory. So there's nothing we can do. We can't make it go any faster than that, because you got to read the matrix in order to multiply by the matrix. So these algorithms that use matrix vector multiply are very popular in scientific applications. Turns out they're also very interesting in a lot of data-intensive data analytics problems where you're computing things like eigenvalues and you're using some kind of a sparse iterative method. So what do you do in a sparse iterative method? You do a matrix vector multiply over and over again. If you're not familiar with matrix vector multiply, sparse matrix vector multiply, think of it as I've got an unstructured graph, and I want to do nearest neighbors for communication on that graph. Each matrix vector multiply step, the matrix, you go back to your beginning data structures class, is just the edges of the graph, and the vector that you're multiplying is at the nodes of the graph. And so we're just going to do sort of a nearest neighbor kind of computation in the graph. In these iterative solvers, you're doing these matrix vector multiplies over and over. After each one of them, you're doing some kind of an operation, a vector operation, such as a reduction operation. So you're adding, say, everything together. There's a couple more things in there. But for our purposes, we don't need to go into the details of the algorithm. So now the question is, what do we do about this? If we can't run it anything faster than the amount of time, the bandwidth of the memory system in order to read the matrix from memory, can we actually reduce the number of messages that we send in these reduction operations, and can we reduce the memory bandwidth requirements? And that is, the question is, can we compute multiple matrix vector products? So AX, A squared X, A cubed X, and so on, which we call the matrix powers kernel, with just one read of the matrix A. So the idea will be, we'll pick up a little piece of A that fits into our fast memory, and we'll compute not just AX, but AX, A squared X, and so on, and then we'll go on to the next piece of the matrix A. So in that way, we'll get K matrix vector multiplies done with only one read of the matrix A, and we can beat our lower bound of being able to only do a matrix vector multiply with one read of the matrix A. So how does this actually work in practice? So let's say that we have a really simple matrix. So as I mentioned, think of your matrix as a graph, because most of your computer scientists, you're probably a little more comfortable maybe thinking about graphs. So we have just a graph is just a line. So it's that thing, the line across the bottom there, which is X. That's actually also our vector. And now because we're going to have a tridimensional matrix, which means that all we have to do in each matrix vector multiply step is talk to our two nearest neighbors. So I can compute AX by looking at the point below me that is the same value and the two neighbors. I can compute a couple more of them up to a cubed x if I have a slightly wider part of the vector and those matrix edge values. I can do this then for a larger chunk of the input matrix, the input vector, and the matrix, and I can get this little trapezoid shape. Okay, so I can read that little chunk of the vector in the matrix into my fast memory, take multiple steps, and compute ax up to a to the k times x in that amount of memory. So in a serial sequential algorithm, and you may have seen these kind of pictures also looking at cache oblivious algorithms for things like stencils. This is showing you for but it's just a one-dimensional sort of neighbor stencil on a line. This is what the computation looks like. That first piece is kind of over there on the side, and then you can compute these parallelograms and so on throughout the computation. In a parallel setting, where I want to be able to take multiple steps on one processor without doing any communication, the computation is a little bit more complicated. We either do some redundant computation, so you see the trapezoid sort of overlapping here, or we can kind of communicate along the edges, but the same idea will still work in parallel. There's some trade-offs in that. Okay, but that was a really simple matrix. That was a tridiagonal matrix, just doing nearest neighbor computation on a line. What if I want to do something like I have an arbitrary sparse matrix, which is an arbitrary graph? So let's say that I want to update all of the edges in the middle of this graph, in the yellow region, all the nodes in the middle of the region, which are the vector elements, in order to compute a to the k times x. Well, what do I need to do a times x is I need the nearest neighbor values around that and their edge weights. If I want to compute a squared x, I need the next layer out, and a cubed x, I need the next layer out. So now this becomes a much more complicated problem in terms of how I'm going to partition up my data structure. I'm going to have to replicate certain things, and I'm going to have to keep track of this in memory. Fortunately, Jim Dem and I, who are working on this together, had a couple of really clever grad students, Moheiden, who did a lot of the implementation work to figure out exactly how to lay things out in memory, reduce the number of cache misses as you're picking up a piece of the matrix and a piece of the vector. It involves some traveling salesman problems in the middle of it, and Mark Coleman, who is doing the numerical analysis, which is going to come up in a minute. So this actually reduces, we can do order 1 data movements for k matrix vector multiplies as opposed to k data movements of the matrix. And similarly, we reduce the parallel message performance that's going to come up from doing k log p to just log p for something like a reduction operation and a reduction tree. So we can take this algorithm, we can put it into one of our favorite iterative solvers. In this case, it's something called GMRes. And I won't really read through the code here or anything, but just to say that there's a SPMB that you can see in the line of the code that's going to turn into something like the matrix powers kernel, where we're computing AB, A squared B, and so on. And then this other thing that I've referred to just as reductions, which turns into something called reorthogonalization, which is called tall skinny QR. And that's a whole other paper and set of papers on how to make that fast and why that algorithm works. But we can go and plug this in. Now, from a compiler standpoint, what have I just done? I've really done this kind of a loop interchange. I've taken my original loop, and what I've done is to say, well, rather than in the inside of the SPMB, there's actually an iteration as well, and I've kind of rearranged the loops so that I'm going to do I'm going to do them in somewhat different order. So I'm going to do a piece of my matrix vector multiply and all of the other parts associated with it. But I have changed the behavior of the program. These are floating point numbers, and I've changed the order in which they're actually happening, although it's correct from a precise arithmetic standpoint. So what's going to happen here is I put this into my GMRes iterative solver, and this graph is showing not performance, but is showing the residual of the error. And of course, if I'm solving some kind of a problem with an iterative solver, the whole idea is to try to get rid of the error. You try to tab out the error. So that's my original GMRes code. Here's what happens to the convergence of this thing if I stick in my new communication avoiding algorithms. So it completely falls apart and is completely useless to us. Now, fortunately, Mark and Jim, who worked on the numerical analysis side of this, said, well, but it's true, but there's actually a different way that you can think about what's called the basis function in this GMRes computation. And you can actually still use that matrix powers kernel and still use tall skinny QR, and you can get your convergence back. So the point of all of this is that you really, what we're trying to do is we're trying to get locality that's up above the level of what we would normally think about as a compiler writer. It's not just loop tiling. It's really fundamentally changing the algorithms, and it's very collaborative. You've got to understand the hardware, you've got to understand the cache effects, and you've got to understand the algorithms. Okay. Now, the next question, though, that may come up with this is, can you do any better than that? Can you, in general, can we do better than these algorithms that I've just shown you, and how do we know? Well, in order to do that, we look at lower bounds. Can we prove something about the amount of communication that's required in order to perform a certain computation, to execute a certain algorithm? And eventually the question is, and we're not there yet, is can we train a compiler to actually do this kind of an optimization? So there's a link to a very long and detailed tech report that I'll refer to a theorem in just a minute. But I will just say that this idea has been around for a long time. There's a seminal paper by Hong and Kung that calls this idea the pebble game. And so we're kind of generalizing that whole line of research in these communication avoiding algorithms. My interest in it actually came from looking at some of the work that Jim was doing with Jim Demel was doing with some of his students, in particular Edgar Solomonic, who is now at ETH. And it's something that they call 2.5D matrix multiply. I will tell you a little bit more about it in a minute, but for the purposes now, all you need to see is that they got a 95% reduction in the amount of communication that was required to do a 2.5D matrix multiply rather than the old algorithm, which is called the 2D matrix multiply. So 2D and 2.5D are the two labels in the x-axis for two different problem sizes. You can see a substantial speed up. Okay, so a whole bunch of, a couple papers later, there's the numerical linear algebra algorithms, and dense linear algebra that they were looking at in addition to the kind of iterative stuff we were looking at before. My interest in it was, I looked at this from a compiler perspective and I said, well, wait a minute, how is it that after studying matrix multiply, which is probably the most well-studied, well-optimized kernel in all of scientific computing and maybe most of computer science, we still had room for improvement. How is it that we could get something to go faster? And the idea behind the 2.5D algorithm is that I'm going to make C copies, some number of copies of the C matrix, and I'm going to compute independently different parts of the matrix vector multiply on those different copies, and then I'm going to add them all together at the end of my answer. This idea, by the way, had been around in previous algorithms. One of them is called a 3D algorithm. The idea of 2.5D is kind of a little bit of a joke. It says it's in between the original 2D and the 3D. It doesn't have to replicate quite as far as the original 3D algorithms do, and we can show that something about its optimality. And that was the other thing that surprised me, is that you could actually prove something about the communication optimality of these algorithms. And the lesson I learned from this also is never waste fast memory. The places where these algorithms help is where you've got a relatively small problem running on a relatively big machine. Where do these come up? So in one of these big iterative solvers we're using in something like a combustion simulation, it turns out that you're running this hierarchical algorithm, and at the bottom you have to do this solve step, and that is, you've already kind of shrunk the problem down, but you're running on a big, huge machine, so you want to use it if you can. And this is actually, the idea here is to take advantage of the fact that there's still memory left in the machine that you haven't used. Okay, so what's behind this 2.5 algorithm, and how can we think about generalizing it for compilers? So the basic idea is to think about the loops for matrix multiply. So in matrix multiply, we've got the code at the bottom is for I, for j, and for k. So that's the 3 dimensions of our iteration space that we're going to go over. We're not going to worry about what the actual expressions are inside of here, but we've got an expression that, what the computations are. There's a reference to the value C of ij, which is something that is every point inside of this cube is one of the computations, one of the little matrix vector, one of the little multiply adds that we're going to do in a matrix vector multiply. And in order to access C sub ij, we have to project that up onto the top or the bottom of the cube. Similarly, the values of the A matrix are on the front and the back, as I've drawn it, and the B matrix, because they've got indices K and J, are at the sides of that cube. So the question is, how can we take this computation we want to do, which is a cube, and divide it up into different, into some kind of subcubes that we will put either each subcube on a little bit of the, in the cache, or we'll put it on an individual processor in a parallel setting. And so it turns out that there's a lower bound, and this idea is due to the other authors, Aroni, Toledo, and Tishkin, that says, well, if I've got this cube, so we're looking specifically at matrix multiply, and we want to look at how do I tile this, how do I break it up into blocks, we can say, well, for a particular piece of the computation, we need to get the projection of that blob of computation on the top, on the front, and on the side. So a theorem that actually goes back to 1949, a basic theorem in geometry due to Luminous and Whitney, says that if I've got some blob, what is the optimal shape for my blob in this thing in order to minimize the projections? So in order to minimize the size of the projections is minimizing the amount of memory that we're using in our fast memory system, and the blob is telling us what shape the tile size should be in the iteration space. And what they say is that it should be a cube. And what that means is that we're going to actually compute on these different pieces of the C matrix separately, and when we want to run this in parallel, we're going to chop all 3 dimensions up across the processors, and that gives us the 2.5D or 3D version of the algorithm. Now, for matrix multiply, we know that it turns out from this result that that we know that the best we can do is n cubed, where n is the size is the matrix dimension divided by the fast memory size, the square root of the fast memory size. So that's the minimum amount of movement required, and we can get that by using these tile sizes that are square root of m by square root of m. In a paper that I referred to earlier, we're looking at, well, can you take this result and generalize it to an arbitrary loop nest? We're working with some pure mathematicians here because we brought in some other kind of mathematics in order to get to this. But the result, which I'll only sketch here, is that the number of words that you're required to move in order to solve a computation where the computation is a loop nest in which you're accessing arrays and the index expressions are some affine, the linear functions of the loop indices, is the number of iterations you're going to do divided by the memory size, the fast memory size is some exponent e. And it turns out that we can determine e by solving a little linear program. Now, of course, again, as a compiler writer, the lower bounds are kind of nice because they tell me when to stop worrying about something, but they don't necessarily give me a useful solution. So it turns out that at least in certain cases, we can also prove that you can compute the optimal tile size. Now, there's ongoing work in here as well. So the long-term goal would be to train the compilers to generate this optimal communication optimal code, both for a parallel setting and for a serial setting. I've taken this with my grad students and applied these ideas to other computations besides matrix multiply, like an n-body calculation. This is just an order n squared n-body calculation. And we show that if you, rather than taking all the particles in the computation, dividing it up over the processors, what you want to do is take the set of particles, replicate it a few times, and then divide it over a subset of the processors. Compute, there again, some of the interactions independently, and then add the results together at the end, very much in the spirit of the 2.5D algorithm. In this case, you're going from a 1D partitioning of the particles to up to a 2D partitioning of the particles, so we call it a 1.5D algorithm. You can see the speedups there. I won't go through the results, but you can look at the slides later to see how you solve the linear program in order to get the lower bound using the theory that I talked about before. Now, the last challenge that I want to mention here is new algorithms and new applications that come from big data in the scientific domain. So mostly what I'm worrying about are things that come from computational modeling and simulation, but there are also a lot of new applications in big data. So I'm going to talk about just a couple of these. The first one is in genomics, which is a problem we've been looking at to do genome assembly. The genome assembly problem, if you aren't familiar with it, is very hard because you're taking little fragments of the genome that have been read by these sequencers, these very high throughput sequencers, and it has errors in it, and you don't know how they fit together, and you're trying to glue them all back together again in order to get the genome. We're doing something called de novo assembly, which means we have no reference genome, which is not the case for the human genome where there is a reference. In a lot of the work that we do at the lab, we don't do so much work on health-related problems. We look a lot at energy problems, so we're worried about biofuels, we're worried about things like wheat and other kinds of plants, how they behave in various environmental conditions, and also really complex genomes called metagenomes, where you actually have a set of genomes. You pick up a scoop of the water in the lake, and you try to figure out what are all the genomes that are in that scoop of water. So in this kind of a de novo problem, you have this very irregular sort of puzzle problem-solving problem, and it turns out that what the biologists used to do is they would buy the biggest shared memory machine they could find, and they really wouldn't even parallelize the code for this one part of it, the hardest part called contig generation, where you're kind of trying to glue the pieces together. But they would build this big, huge hash table in shared memory, and then they would just insert things into it, and then they could put the pieces together. So there's a paper if you want to hear the details about this. The point is random access into memory. I can only do it in shared memory, so we said, well, wait a minute. We've been using these ideas in high-performance modeling and simulation called PGAS languages. Let's try this for genomics, and it worked extremely well. there's also another line of this on the algorithm side. I should say there's a lot of clever algorithms as well as software rewriting that goes into the performance result. But the performance result was that it used to take them 44 hours to do contig generation on the human genome. They can now do it in 20 seconds. The wheat genome, they had never assembled before. There was a little competition going on, and one other group assembled it using different techniques, kind of chemistry techniques, where they divided up the genome in a certain way in the laboratory before they did the assembly. And ours, which was a full de novo assembly, which we did in 32 seconds. So this is the kind of thing that changes the questions that scientists ask. It allows them to explore the data in a new way, and so on. The second example I'll give is, well, really kind of two examples together. One is from carbon flux data sets, where you're trying to measure all the carbon in the atmosphere. Deb Agarwal, who's one of the science managers at the lab, has been working on this for a number of years, and she said one of the big problems is the getting rid of the noise in the data. Sometimes call this a dirty data problem. Her problem is particularly dirty because one of the places the noise comes from is pigeon dropping on the sensors. So you've got these sensors out there in the real world, and pigeons drop things on them, and then the data gets all messed up. So you have to figure out how to remove the noise. And there's algorithms for that. However, it's also important to remember that a couple of famous scientists, Arno Penzias and Robert Wilson, also had a problem with pigeon droppings in this antenna that they were using, and they scraped it out a couple of times, tried to get rid of the pigeon so they could actually get an accurate picture of what the microwave looked like in the looking in the universe. And what they were looking for was what they found was a signal in this. And they kept thinking it was from the pigeon droppings, and it turned out there was actually a signal in the pattern that they were seeing in the antenna that was the cosmic microwave background, which is actually a blueprint of what happened right after the Big Bang. So the moral of this story, when I kind of put two of these together, is be very careful when you throw away the noise in your data, because it could actually be the signal that you're looking for in your scientific experiments. Data rates for scientific instruments are growing up dramatically. They're still on a Moore's law curve, and they have not yet reached heat density limits for things like CCDs, charge coupled delays, which are inside of telescopes, and they're inside of things like these synchrotrons where you have detectors, and so on. And the genome sequencers, you can now get your genome sequenced for about $1,000 with the latest Illumina sequencer. So this graph, and I just want to be very careful, this is just a plot showing the average growth rates of these different kinds of technologies over a period of time. It's not actual data on this slide, but from the average growth rates, you can see the difference between those sequencers, the detectors, and then the green curve there, which is processor performance, and then way down, and then down below that even is the memory performance. And so all of these, or memory density, sorry, all of these things, the ability to collect data is growing much faster than our ability to compute on it. So what you saw in the genomics example, and comes up in a lot of these data problems in science, but also in other areas, is that you have much less structured data. In the scientific simulations, for the most part, we're doing physical simulations. So you're taking, whether it's the globe and dividing it up into pieces, and you have a fairly regular pattern of what you're going to do. There's irregularity that comes up because of things like clouds or hurricanes, but you fundamentally have a physical domain that you can use to map that onto a parallel machine. In the data analysis case, in many cases, the whole point of what you're trying to do is to figure out the structure of your data. What does the graph look like for Twitter? What does the connectivity graph of the web look like? What is the genome? How do the different pieces of the genome fit together? So these ideas of global address space programming are actually even more valuable there, because the idea of trying to do this coordinated send and receive is even more awkward when the data is very unstructured, because you don't know what you want to access when. Part of what we want to do in science and the data of science is to make the scientific results highly available to the community. We're building things called science gateways at NERSC, which are web portals so that you can access, for example, field compost 20th century reanalysis climate data. You can access simulation data for materials modeling. You can access various data sets from the Genomics Genome Institute and so on. So this, I think, is really going to change the nature of science. It means anyone, anywhere can access data from some of the biggest scientific instruments. And so that kind of big team science and that big instrument science that I talked about before is the hallmark of labs like Lawrence Berkeley National Lab are now also available to all of you here in all of your universities, because the data becomes accessible. And my view of the future is that eventually science, anyone, anywhere can access the scientific results of the latest experiments and the most complex theories that are produced in simulations. So I'll end with a little prediction for the future. So looking at 2031, what do things look like for a scientist in 2031? Well, first of all, no personal or departmental computers, so all your clusters go away. You're either computing in the cloud, you're computing on a supercomputer, or you've got your little input-output device. So this is maybe back to the future, if you will, but you don't have personal computers anymore. You don't log into HPC facilities. You just go through web interfaces and you ask questions, which automatically get executed for you. I wouldn't actually be here. I would have just sent my my little telepresence to give this talk, which wouldn't have been nearly as nice in terms of being able to see Go, but would have saved a lot of travel time. We have MOOCs that are teaching millions of students, very controversial in terms of exactly how that will work, but that's one possibility. Even things like proving theorems, you may do it in a community of people you don't know online already. That's happening today. Laboratory work, like even doing experiments on mice, is outsourced, so some not necessarily on the same facility as scientists are at, and all of us can access experimental facilities remotely. And eventually all the data becomes science. So the big data and the team data and the team science that I talked about before become much more democratized because everybody anywhere can access this data, but also become part of a team in a large scientific project, regardless of where you're located. So with that, I would like to end, and thank you very much for your attention.
Thanks, Kathy, for a wonderful talk that starts with big vision, gives a lot of details, and again ends with big vision. Now there is time for a few questions, and we would really like questions from the back. Students, and can you have more lights in the audience, please? And there are volunteers with mics around. Just raise your arms and hands and ask questions. The first question is the hardest to come out. So I'll ask the first question. You're talking about all the matrix operation. When the data becomes so big, the matrices also become sparse. So how do these scale to come to sparse matrices?
Right. So, so that's a really important point. As we see the size of the problems that people want to solve get larger and larger. If you're running something like an order n cubed algorithm like dense matrix multiply, you just aren't going to be able to wait for the answer even on one of these fast computers because you've grown the size of the matrix that you're using. So instead, what we're seeing is a real trend towards adaptive methods. So adaptive meshes, rather than that nice uniform, soccer ball around the globe, we're actually putting really fine meshes right around the coastline and really coarse meshes over, where there's land or something like that. So you see that kind of adaptivity. What that means is they become more irregular sorts of computations, which means that you run into some of the kinds of problems that I talked about in the data analytics, where you don't really know when to communicate. Things are not just running sort of uniformly together. So sparsity and adaptivity are both increasingly important.
I don't have the mic, so let me ask the next one. Okay, so I have a slightly tangential question. You talked about primarily algorithms or problems which generate lots of data and then consume them. And in the end, you talked about some problems which also consume a lot of data, but also do a lot of computing on them. But you didn't talk of any of the architectures which are in, say, Google, the MapReduce, Regals, the everything in between, and with the flash data center, GPUs becoming part of the stack. Is there a convergence, or are these two worlds going to remain?
Yeah, it's a great question. I definitely see a convergence. I think that it's unfortunate maybe that the HPC space is viewed as so specific to science, and the big data space is all about data analytics, and not so. I mean, there's some examples of science projects in that, but really a lot of focus on things like text mining and kind of business analytics and things like that as the applications of it. So I think it's really two different communities. But if you look at that, I mean, what we're seeing is people use eigenvalue problems all the time in data analytics, and you talk to the vendors. I mean, companies like Google, they won't say very much about exactly what is in their data centers, but they will say that they care a lot about the bandwidth of the network. So I think that as you try to scale these problems up, and we know some of these algorithms, like machine learning algorithms, I'm working on a problem in stochastic gradient descent. This ability to do sort of fine-grained communication is one of the things that will be important in that. So I do see a convergence in the architectures between those. Yes, we're seeing GPUs being used for deep learning. We're seeing, all of those kinds of things. So I think that's where HPC and large analytics are going to come together. We also see, I kind of like to divide the world up into the irregular and the regular computation. So both in science and in cloud sort of workloads, I think you also see a lot of massive high throughput, independently parallel computing. So serving web requests is not a highly parallel problem, but it is a massive volume problem. And in science experiments like the Large Hadron Collider, they run massive amounts, a number of analysis problems that are all independent. And so I think we see that independent workload and that tightly coupled workload. We are studying, whether you can have one architecture for both, but I see that the need for both data analysis and the science to have both.
So you are not very positive about accelerators in your architectures. And though you are saying that it's okay to have heterogeneity, it's also you are also saying that you are okay with not having cache coherence across processors that will be mixed. So in that setting, so why are you not very positive about accelerators? Because clearly they give you a very high power performance compared to computing that we see.
Right, so let me be clear about that. And first of all, in some sense, I see heterogeneity as a necessary evil, not something that I, as a programming model designer, like to have in the system. But a lot of these effects are coming up because of architectural constraints or power constraints. So I see that, as I said, that the need for fine-grained processors and coarse-grained processors, the question is how they're hooked together. And so when I use the word accelerator, which may not be what you mean by accelerator, I see them as separate chips with a pipe of some kind between them. And that runs into all the communication problems I talked about at the end of the talk. I mean, even if it's better than something better than PCIe or whatever, it's still fundamentally going off chip and going to another chip. So that's what I don't like. But it may happen for market reasons anyway.
On the back, people will be
somebody who's still in school. Somebody who's still in school has to answer a question.
2031, you will be starting your career.
That's right.
People like that. Anybody? Come on. You pledged to Srinivas something.
They're all busy saying.
Now I have to get back to Srinivas for the question. Okay.
This goes back to the earlier question. So I have got some comments from the community of HPC sometimes that the work on algorithms they produce takes 10 years to reach the Hadoop and the big data community. What's your comment on that?
You're saying the work in the HPC community takes 10 years to get to the Hadoop big data community? Yeah, I guess I hadn't thought of it in that particular way. I think that, there was this horrible split that happened when the big data thing became popular, and they were just, we are not scientific computing people, we are big data people, and it's completely different, and that was a real problem. I don't think that 10-year lag, if that's really what it is, will persist, because I think that a lot of HPC people are working on data problems, a lot of data people are looking at HPC techniques. There may be a lot of rediscovery of HPC ideas in big data, and that I worry about a little bit, because that's kind of a problem in our field in general. So all of you who are students, remember that part of your job is to also read the related work, and you need to maybe talk to somebody in a different part of the discipline. If you're working on big data, go talk to an HPC person and say, well, what's related work that you think might be relevant to the problem that I'm working on. So maybe we look to the students in the back of the room to keep that 10 years to make that go down. But I agree, there's a big issue there, which is the gap.
Question from the back again. Back people get the priority. Otherwise, we'll go to the question here, third row.
How do you think the domain-specific compilers, the questions here, what is the role of domain-specific compilers in this whole thing? Coming to science now, domain-specific languages, how it's going to affect?
Yeah, so domain-specific compilers are really interesting, and domain-specific languages and all of this. I think this, when I talked a little bit about automatic performance tuning, that's the way I see that we kind of inoculate the applications people from what we don't know about the future architectures. We say, well, you write a domain-specific compiler that has the computational kernels for your scientific domain, or even your algorithmic domain, whether it's graph analytics algorithms or or matrix algorithms for doing data analytics, and you write a code generator that generates really good performance code for GPUs and really high performance for the Xeon Phi. And then if somebody says, oh, we've decided that the future is FPGAs, it's probably harder to generate that kind of code, but it's at least a kind of contained problem. It's a way of putting some kind of isolating where the code has to be changed. I think it makes it a more tractable problem. It is also the case, one of the reasons we've looked at domain-specific languages in the CGIS project for things like stencil computations, because in stencil computations where you're operating on a grid and then you want some operator there's so many different operators that people use. And as a computer scientist, I say, well, just pass the operator into the library and we'll optimize it for you. But the problem is you need to see the operator in order to do the optimization. So that's what DSL, I think, is really important. Things like linear algebra and FFTs can be encapsulated in a library kind of built once, but for things like stencils, you really need something like a DSL approach. So, and we are seeing these also in the data in the cloud community. They're building, and there's DSLs being built out there as well. So, not a crazy idea.
Hi, I'm Prahlad Deshpande from IBM Research. My question pertains to the last 2 points that you have brought forth over here of democratizing research and science and stuff. We are seeing this happening in the open source community a lot, and it's from open source coding, things are moving to very open thinking and research in that sense. So my question is, do you think that all this business of publishing in conferences and a few people reviewing what you have to say about a certain thing, all of that is going to go away, or are we going to still have that? Are we still going to have that business going on in 2031?
I think we will still have conferences, and I don't think we will all send our avatars to conferences, because I think that really important connections happen informally at the conference. We're eventually going to get to finally have this morning, and that will be, it's the informal connections that you make to people and things like that. So I don't think conferences will go away. I think the nature of what it means to publish may change, and I mean, we're already seeing this with people just putting papers up on the web and then having them be highly, my most highly cited paper is a paper that was never published as a journal or conference paper. It's the Berkeley View paper on parallel computing, the tech report, and more citations than anything else. So, that's definitely changing the, what it means to publish papers. I kind of wonder, and maybe this will scare people, if we're going to end up with something like Yelp, for papers, which is John Hopcroft says this is a really important paper, and you go, oh, I better go read that paper, because that if you listen to authorities on it, people will develop their authority. That's maybe it's a sad projection of the future, but I do think that's going to change.
I'm going to be like airlines. Any row number 15 and above. Any questions? Yeah, there. Sorry, Alex. Please stand
Hello.
up. Let's see
I'm
you.
an undergrad student, and I'm yet to start any sort of professional career. But I wanted to ask if there is any scope of open source projects going on in the area that you just talked about.
So open source projects going on, yes, I would say almost all of the code in scientific computing is open source. And the reason is because you can't make money doing scientific computing. So this is one of the things I wanted to tell all of you who are computer scientists, that these are great problems to work on. You can have a really big impact on the world. You probably don't make as much money if you go off and do game programming, if you work on climate modeling, but you can maybe really have a very high impact on the world. And yes, the climate codes are open source. Most of the languages, the UPC compiler that I talked about, there's 2 open source versions of it, the one that we have from Berkeley, and there's another one from the GCC-based version of it. The data analytics side, there is the AmpLab project, which has the Berkeley data analytics stack. All of that, at least initially, is open source. There is a company now that's kind of continuing on in a commercial setting, but there's a lot of open source versions of both data analytics and scientific computing software.
And how can we reach out to them?
Let's see, I guess if you're wondering about how to use them, if you send me an email, I will try to answer it. I'm not always good about it. You can find me on the web pretty easily, so send me an email and I'll try to at least forward it to the right person who can answer the question for a specific thing. But you can do a Google search for Berkeley UPC or let's see, the Berkeley data analytics one. Do a Google search on AmpLab, AMP LAB, and for some of the other scientific computing stuff, I probably need to give you specific pointers.
Okay, we'll take a question from the front row. After that is the turn of row 10 and above. Oh, no, there's none. Okay, mic is gone. You want to ask a question? Yeah, go ahead.
I just wanted to continue this issue a little bit about high performance computing versus cloud computing. And I think one very significant divergence is in stream processing and real-time analytics. And I think that, you know, there's an emphasis in cloud computing that's just not a problem in HPC at this point.
So, so I don't actually, it has not been a problem in HPC, and it's the way the HPC centers are set up right now. One of the things that NERSC is working on is they have done real-time feeds. This is a really cool demonstration they did. Somebody's printing photovoltaics up at the advanced light source. They're imaging it. Data is streaming in real time to NERSC. Actually also streaming in real time to the supercomputing center at Oak Ridge. At NERSC, they're doing some kind of front-end processing to try to figure out whether the experiment is collecting what they want. They have a web portal. Actually, somebody else used that web portal in Europe on their iPhone when they were on a train, so you can sort of see your experiment running in real time. And what they were doing at the Oak Ridge machine was running computer simulations to try to interpret the data. So they're solving an inverse problem. They say, I'm looking at this thing as material. They're watching the photovoltaics dry. They're trying to figure out exactly what the structure is. So you're using these supercomputers. Right now, I will admit, we're doing it kind of by hand by saying, call the guy at Oak Ridge and say, can we reserve your machine for an hour? Actually, they reserved it for a day, and it wasn't quite enough compute time. They needed about 50 times more. But anyway, yeah, that is changing. I will also say, to me, the big difference is the economic model and that kind of scheduling model of the cloud. We see that the HPC systems are actually, we run NERSC at about 1/3 of a cent per core hour, so very inexpensive. People think clouds are cheap, but 10 cents is really a lot of money for a core hour. Maybe it's a little less than that now in the cloud also. But anyway, the difference is, though, they run their machines at less than 30–40% utilization, and that means that they can give you on-demand access. We run the supercomputers at 95% utilization, which means you've got to make a reservation to use them. So that's something we have to think about. That's a kind of a policy question too. Are we willing to let our supercomputers remain 50% idle to make sure that when somebody wants to use it, they can use it? That's not something that the government has been willing to do.
One question at the back. Yeah.
Hi, ma'am. Ma'am, as you know, the data analytics, Hadoop has served the purpose of data analytics for a long time. But as you know, recently the MapReduce algorithms are not that efficient. And recently, Google came out in the interview and they said, okay, MapReduce is not the thing, like it's not really like efficient. So how do you see the future of Apache Hadoop? And I'm aware of the Apache Spark project with AmpLab. So how do you see that project in like comparison to Apache Hadoop? Like what's the future of these projects?
Okay, so I'm not sure I entirely understood the question, but I think it was looking at the inefficiency of things like MapReduce. Is that?
Yeah. Recently in an interview by Google, they said that MapReduce is not that efficient, and Apache Hadoop is basically not able to do this efficiently. Recently, also I've heard of that AmpLab has been working on something called Apache Spark. It's really scalable, but okay, how do you compare these two projects, and where do you see the future of these projects? Like where are these two going?
Okay, so I'm going to step back and give kind of a philosophical point of view on this. So the AmpLab developed a version of the MapReduce model called Spark, which is much faster than the original Hadoop implementation. The reason is because you leave the data in memory, which is no surprise to an HPC person that you don't want to put the data on disk if you wanted to run at any reasonable speed. What is different in kind of different perspectives was the MapReduce people came from a perspective that machines fail all the time, and you need to be able to always recover data from them. So you're putting the data on the disk. For the most part, Spark gives you that kind of resilience model, but leaving things in data using other clever algorithmic tricks and so on. The HPC space is really struggling with what to do about resilience. Like, oh, we have to worry about nodes failing all the time. They dump all their data out in checkpoint files every once in a while. So there is a difference. I think there's learning that can happen in both directions, but I think there's a lot more potential for performance improvements inside of things like Hadoop and MapReduce, and even inside of Spark in the in-memory version of that. As the communication models, they're using TCP. What can I say? There's definitely performance to be gained in that.
Okay, so
thanks, sir.
We'll take the time. We'll take one more question if it's only from row 20. No more. Otherwise, okay, last question, not row 20.
A very nice talk. I'm a grad student close to completion. So I've been hearing a lot about this neuromorphic computing and brain-inspired computing. So what is your take on that?
Right. So neuromorphic computing, quantum computing, reconfigurable computing, special purpose computing. I think that all of these things, analog, DNA computing, even. This is a sign of desperation in the field because we are running out of Moore's law. So we kind of got over the multi-core thing and the inability to make single processors go fast, but we really are going to run out of the ability to put more transistors on the chip. And so I see neuromorphic computing, at least the specific things that I've seen in neuromorphic, as kind of special purpose architectures that are very good at executing particular computational patterns like learning, neural networks. Okay, so that is, that may be an important model. The Anton supercomputer, very good at doing molecular dynamics. So we may see more special purpose computers, which were not cost effective in the past. But if we can't make general purpose computers faster, then there will be more motivation and more, it may make more sense to actually do something more special purpose, like a neuro-inspired computer of some kind. We are also looking at trying to understand more about the brain and understand whether there's a model of computing related to that in the work of the lab, but we're just starting that. Okay.
So let's thank Kathy Yelick once more for a wonderful talk. And given these things, from what I understand, Professor John Prof is going to talk about, she has set up the world very well for the kind of thing that I think he's going to talk about. Anyway, I don't know what it is, but it's my pleasure to hand over a small memento to Kathy on behalf of ACM India. And she really had to work her airline schedules, etc., due to some unexpected event. So thank you once again. And yeah, and do come back for Professor Hopcock's talk. It's we have at 2 o'clock, but be here 5 minutes before. We have enough time to have lunch.
And one for Professor J. Narayana.
Thank you.
Thank you, sir. Thank you. We'll be back here at 2 o'clock. Now you can proceed for lunch. Lunch will be served in the food court. It's a pandal. Our volunteers will help you and guide you in that. So please be back by 2 o'clock.